Hello, everyone. Today we're going to start talking our notes about projectile motion. So you should see this slideshow that is posted. I believe I have it, gave you guys the completed version other than the workout problems. So free response question, you guys have a bullet being dropped from the same height at the same time in which a bullet is fired from a gun. The drop bullet falls straight down where the bullet fired is projected forward at a speed of 370 meters per second, which is about 828 miles per hour on completely level ground. Which one hits the ground first? So they drop a bullet and then they fire a bullet. I had assigned the Mythbusters Knock Your Socks Off, where they go through and they do this experiment. Now, in the ideal case, where there is no air resistance, so it is not going to be any air that is falling through, it doesn't matter if something is kicked sideways, if something is dropped straight down at the exact same time, gravity acts on both of those objects the same. Doesn't matter that something is going sideways, gravity acts the same on all objects. Earlier this year, I assigned the video for you guys to watch where they took a feather and a bowling ball and sucked out all the air in this chamber and dropped them both at the same time. And they fell down together. Without air resistance, gravity acts on all objects the same. So just because this one shot sideways doesn't mean that gravity is not going to pull it down the same as a bullet that is not fired. And that was the point of you guys watching that episode first. Okay, two terms to be familiar with: horizontal versus vertical. Students usually always end up confusing the two. Since we have two different motions that are going on at the same time, we have one motion that is horizontal and we have a different motion that is vertical. And we'll talk about those a little bit more in depth. But horizontal goes left and right, vertical goes up and down. A way that I was always taught to remember that difference is whenever I'm looking at H, I have two vertical lines and I have to cross the H, which goes left and right. Or if I'm looking out on the horizon looks flat, straight left and right. Whereas vertical, I would be looking up or down. Now, why do we have to define those two? Well, that's because with projectile motion, there are two different motions going on at the same time. And those are the two that we have looked at so far this year. Horizontally, we have constant motion. So that means that whenever a projectile is fired, whatever motion it's moving with horizontally, that is the same motion it has the entire time that it is traveling through the air. But vertically up and down, it's accelerating by gravity. And gravity is going to change its velocity every single second that it is up in the air. And it's going to be pulling it back down towards the ground. So as I take a look, some key terms to be familiar with: the path a projectile travels through the air, that is known as its trajectory. So if I see an object that's flying, this blue line right here, this would be what's called its trajectory, the path it takes throughout the air. The shape of the trajectory is a mathematical term. It is in the shape of a parabola. And what that means is it mirrors itself on that vertex, the point where it is the highest. So if I have something in either point, if I look here with this football, where it's going up versus coming down, it would have the same speed at the same height. But it's just going to have a different direction, where one's going up, whereas on the other side, another one's going down. The other term that you should be familiar with on this page would be what's called the range. The range is the horizontal distance that the projectile travels. So it'd be from where the punter kicks the ball with his foot, and the range will be measured to where the ball lands. Okay. But you will need to know those three vocabulary words. Again, the path the projectile follows is known as trajectory. The shape of it is in a parabola. And the horizontal distance, that is known as the range. Now, there are two types of projectiles that we'll look at. There are horizontally launched, so I'm just shooting it straight sideways. I'm not aiming up or down at all. The other type of projectile would be where I actually do launch at an angle, where I'm shooting it up first and then it has to come back down. So maybe I'm shooting a basketball. Maybe I'm throwing a baseball. I'm hitting a golf ball. Think of anything that happens to be thrown in the air. Over here, it's like maybe I'm shooting an arrow, maybe I'm shooting a bullet. As soon as that gets released, gravity starts pulling it back down again, and its path will be curved. Now, what this slide here happens to show, this is a projectile that's being fired, and at each individual point, that is a certain amount of time that has passed. And if you notice, those lines are directly, those two black dots are directly above each other. If gravity were to pull just straight down, if I just let go of that cannonball, it would just fall. If gravity didn't exist, on whatever direction I shoot that, it would just keep going that way forever. But since gravity is pulling it down, it's going to start going faster down, faster down, faster down, faster down. It's accelerating vertically, but if I'm looking at that dot, it's going that same horizontal distance left and right each second. And I can use a little simulator that I can show you guys this too. You guys will be using this website here for a virtual lab a little bit later within the unit. If I drop a ball straight down, I can measure how long it takes by pulling this over and recording the time. If I increase the speed a little bit more, now I'm shooting out, I can still measure how much it is. Now, why did I bother with the simulator? I like using the simulator because it will show these vectors, those arrows. Now let me slow this down. So when I fire, if you can take a look here at the green line, oops, can't do that. Can't zoom in. All my arrow is horizontal. That's because it's just coming out of the cannon. Gravity hasn't started pulling it down yet. But as I start to step through, there's a vertical line that's appearing here. In that vertical line, I'm recording the velocity. How fast is it moving? Horizontal, that line doesn't change. That will stay the same. It's going 18 meters per second forward every single second that that projectile is in the air. But as it is falling, it's also accelerating back down towards the ground. It's in free fall, our last unit that we just finished. And this is just going to keep getting faster and faster and faster until it hits the ground, and then it's not going to be moving anymore. Next slide, view. Okay, back to the slideshow. Maybe. Okay. All right, so how do we do the problems here? So basically, we're going to be combining two problems into one. We have two equations. Both are ones that we have used already. The biggest thing with this is making sure we're identifying one of two things correctly. We have our range, which is distance in the x direction, left and right, and we have our height, which is our distance in the vertical direction. Our dx, horizontal, our dy, vertical. And we have two equations where we have distance vertical and we have distance horizontal. There's two equations that we'll use for these. Typically, we'll have to find out what the time is first, then plug it in and solve for how fast does the projectile need to be moving. So let's go ahead and work through this problem. A girl throws a ball straight out from a bridge with a height of 20 meters and lands 11 meters from the base of the bridge. How long does it take the ball to hit the ground? How fast is the ball moving? Okay, so there is a bridge with a height of 20 meters. If I'm thinking height, I would look either up and down. That is my vertical information. That would be the 20 meters. And that goes over here for dy. It lands 11 meters from the base of the bridge. A lot of times it'll say away from something. If it is away from you, that is how far horizontally you're located. That is my distance in the x direction. Now, as I take a look, if I'm given the height, I know everything in here that I can find. Although there is one thing that's not listed in there, and that is this value right down here, g. Just like we were using for the last unit, g is 10 meters per second squared. Please make sure you're using this value when you're plugging in for g. Asking Google will not work because Google uses a different value. It is more specific than what I use in this class. So if I'm going to find out what is the time right here, time is equal to the square root of 2 times 20 divided by 10. With my computer calculator, I need to do everything underneath the square root first. 2 times 20 divided by 10. So that's given me, I need to take the square root of 4. When I take the square root of 4, that's going to give me 2 seconds. Over here, to figure out how fast does the girl need to throw the rock in order to get it 11 meters away? Well, the distance, 11 meters, divided by my time, 2 seconds. And that's going to give me 5.5 meters per second as my answer. And that's how fast it would need to be moving. Take a look at example number 2. Greg decides to throw his physics book off a bridge that's 45 meters high. 45 meters high, I would be looking up and down. That is my y direction. It lands 40 meters away. Away is my horizontal distance, also known as the range. I'm also going to use that g is 10 meters per second squared. How long does it take the ball to hit the ground? Using my equation for free fall. 2 times my height divided by g. Square root 2 times 45 divided by 10. 2 times 45 is 90. Divided by 10 is going to give me 9. I can't forget that I still need to take the square root. When I take the square root of 9, I end up with 3 seconds. Once I have my time, how fast did he have to throw the rock? V equals dx divided by t. Distance divided by time is my speed. My horizontal distance was 40 meters divided by 3 seconds. And I would guess this is going to be 13.3. And that's how fast it would need to be moving. Just reviewing with horizontally launched projectiles. Whenever something is up here at the top, all I have is Vx. Vx stays the same the whole time. Up here, there is no Vy. All of it is vertical, or horizontal, I should say. Here, I am getting a bit of a Vy that's coming down, but right before it hits the ground, this is where it's going to be traveling the fastest, right before it hits. And that's because it's had the most time to fall. But that is horizontally launched projectiles. Slowest at the top, fastest down here at the bottom. With angle launched, all these here are still Vx. And Vx is still constant the whole time. So whatever motion I'm going forward, that's the motion I'm going to have the entire time that it's going horizontal. But vertically, the lower it is down here after it's being shot, this is traveling up. Well, halfway up, it's not going quite as fast. Up here, there is no Vy because it's going to keep traveling up until it runs out of speed. Then it's going to come back down again. And if it's at the same height, this vertical velocity piece is going to be the same. Same thing down here, Vy. The lower it is, the faster it goes. But horizontal motion is constant the whole time. Okay, projectiles launched at an angle, did that one. Greatest range. The greatest range occurs whenever a projectile is launched at an angle of 45 degrees. That's because your vertical and your horizontal components, that ends up being the maximum whenever it's kind of right in the middle, halfway up, whenever you're aiming. Now, the other key bit of information on this slide has to deal with complementary angles. Complementary angles are two angles that add up to 90 degrees, and they have a really interesting feature. If you notice, 15 and 75 degrees land in the same spot. 60, 30, they land in the same spot. If I go over to the simulator that I was using, I shoot one at 25 degrees. If I shoot one at 65 degrees, look where it lands. The exact same spot. And that's because while this one here, the one that gets shot lower to the ground, it goes really fast, but it's not really in the air very long. Whereas the one that gets shot up in the air, it travels a lot slower forward, but it's kind of like the hare or I should say the tortoise from the story of the tortoise and the hare. This guy might go slower, but he goes a little bit longer, so he ends up traveling the same distance. Whereas this one goes quick, but a short time. But they'll still land in the same spot. So what will we do with angle launched? All we'll do is figuring out what angle the object is going to land. So what angle would a person have to throw a ball to have the same range as a football thrown at 20 degrees? If this is my angle equals 20 degrees. That angle plus the other one has to equal 90. Angle 1 plus angle 2 equals 90. So if this angle is 20, angle 2, I would subtract angle 2 would be 70 degrees. At what angle would a person have to kick a soccer ball to have the same range as something thrown at 10? 90 minus 10 is 80 degrees. And that's all the more math we will do with angle launched. All right, and I believe that completes our notes.